Welcome to my talk. My name is Morten Arngren. I work as a lead data scientist for Adform. I'm here today to talk to you about some of the stuff we do, the cross-device tracking algorithm. So my background is mainly in data science. I'm not much of a back-end engineer. I think if anyone gave me keys to production, I would probably destroy the whole thing. So how many of you guys are data scientists or machine learners in that sense? One, yes. And how many are back-end engineers, developers? Perfect, nice. So the talk today is essentially seen from sort of a data science story. It's seen from a data science perspective. The question is essentially, how does a team of data scientists go about researching and doing stuff? So I will try to do my best to take you in the engine room. I'll talk about that later, and also connect that somehow with the back-end world. Usually when a team of data scientists create some stuff, they start with a white piece of paper and a pen. They do some crazy stuff. They deliver something to the back-end guys. They look at it and think, Jesus, have you been drinking? So usually there's a kind of a friendly conflict between what comes out of the laptop from the data scientists and what is supposed to hit production afterwards. So I'll address some of these points. I'll try the best I can to also take you through the story of how the things that come out of data scientist group. Why does it look like the way it does? What are the obstacles we found on the way? And what are the challenges, and how do we choose to solve it? So first of all, I'll take you to the engine room. Usually when stuff is delivered out of data scientists, it's usually perceived as a black box. And you put stuff in, you press the green button, something comes out, and we're good. So I'll try to take you into the engine room, open the black box a little bit, take you in it, and see what goes on. So this is a project that started in last year, in January, and we worked on it for, I don't know, 6 or 8 months, I think. Then we went on doing something else, and now here in August, we reopen it again and revisit it with some new data in there. So actually, the whole story is about these two kind of separate projects combined. I'll do my best to try to elaborate how that works out, so hopefully you can see how things work. And more interestingly, there's also the whole scalability issue. One thing is that it actually works on a laptop. That's fairly straightforward. But once it hits billions of events or data sets out on the real world, things change. So I'll try to elaborate a bit about what the collaboration is between the data scientist team and our back engineers team. And unfortunately, this is still under development, so I don't have a finish line. There's still stuff out there that we don't know of how to solve. I'll take you all the way up to the point where we are today, and hopefully we can push the last part afterwards, but I can't show you sort of the final flag at the end, I'm sorry. So let's take a step back and just look a little bit into what Adform is, the whole ad tech world. I know you know the booth outside, that's us with the big boxes you have to tilt over and all that stuff. When we get back home to the offices, we do something a little bit more complicated. So imagine you are an advertiser, you invented a rocket, you have an ad, you want to push that to the world, you want to advertise, maybe people buy the rocket, who knows. At the other end, you're a publisher, for instance, you own a website with news on it, you have tons of traffic, you have tons of banners everywhere, but nobody comes in and puts an ad. So Adform, as you can probably guess, sits somewhere in the middle with a whole range of complicated stuff. And we connect the dots and make sure that the advertiser has an opportunity to make an ad, and the website publisher has an opportunity to get the placement and earn a buck, and hopefully have a free website. So I won't go into details with all the different parts. This is just to show something complicated happens on a higher level at least. And in numbers, we are mainly in Europe, a little bit in Americas, Asia, 800 people. 360 developers. Most of them actually sit just around the corner in less than a kilometer from here. And we're hiring, by the way. We'll get back to that. Next slide. Here we go. Okay, so to define the problem of what we're looking into, let's try to define the stage of what it is that we want to solve. We have the white piece of paper, the pen. So what is the problem that we're looking into? So if we take a step back, we can imagine a guy, a ghost, some sort of user. He goes into his laptop. Throughout time, he uses his different devices to check out news, websites, whatever he does on the internet. For every session, he gets a cookie. Sometimes the cookie lives a long time, sometimes it lives short time, depends on how the setup is, and sometimes you use different devices for it. Now in this particular context, often we denote sort of cross-device as being precisely across devices. But sometimes a cookie can also live within the same laptop, whatever you have, die out and you get another one. So even though we call the talk cross-device, we still sort of include the whole problem of cookie churning. So even though we call it cross-device, so that's more or less the same thing. So the basic idea is that we start with a gigantic pool of cookies, and we need to figure out which of these cookies actually belong to the same user. Sounds super simple, and it probably is if you have small data sets, but when you've got big data sets, things start to change a bit. So that is kind of the main part of things. How do we figure out which cookies belong to the same user? We don't care which device he uses, we just need to know this cookie belongs to this particular user so that we can keep his history and don't lose his interest throughout time. So that's kind of the basic idea. Fortunately, there are a number of companies out there who does this. Some of them do it for a living, and obviously Adform want to be part of that. We are already in the ad tech business. It seems only natural for us to contribute in this sense. So let's talk about the data. So we need the cookies. That's kind of our starting point. We need some data to figure out what is associated to these cookies. How do we get some data out of it? Essentially what we want to do is to build a machine learning model that takes in that big pile of cookies and spits out these connections between cookies. So the data that we have can, for the moment in this first trial, is cookie, obviously, the time, location, based on the IP, operating system, use agent, device, and 3 dots. You can possibly put in more if you want to. We'll get back to that at the end. So that's kind of the metadata. That's the raw part that we have associated to each cookie. The problem is, if we want to build a machine learning model to learn this, we need labels. Otherwise, how would the machine learning model know which cookies actually belong together? To this end, there are some external providers as well that does this also for a living. In this case, we chose YouGov. They have a reasonably good data set, at least in the beginning. They provide us roughly with around 700,000 events per day. We got an internal database, Vertica, around the bit responses, which essentially contains all this metadata that we need. We got 1.5 billion events per day, so it's pretty big data sets as such, but once you start joining them, you realize that it actually shrinks down to not that much, mainly because we're limited by how many cookies we actually have ground truth of, right? So we got 2.5 months of data, 7 million events to do some filtering. We got roughly 74,000 profiles coming out. So at this point in time, when we get the data out, one of the first things we often do, or we should do as data scientists at least, is to not just take the data, put it in the model, press play, and see what happens. So the first thing we do, we actually spent a few days on it, is to take the data out, shake it a little bit, kick it a little bit, set fire on it, and twist it and see what it can do. And also make some distributions out of it. So you have this idea of, when I put this data into the model, what comes out? What can I expect to come out? If the data set is full of outliers, for instance, then probably my model will do the same thing. So in this case, we did many different types of analysis. In this case, we looked at the singletons. In this case, we got 20% of singletons. So imagine you have one cookie, one device, one cookie that never gets renewed, that is just stays, that doesn't connect to anything, which means there's no information in terms of associating it to other cookies. There's just one, which in this case means our machine learning model has nothing to learn from this part, right? So the higher the number is, this number is, the more concerned we should be. So essentially for training, we need to get rid of this and focus on the 80%. So that's the first thing we're doing, getting rid of stuff that we can't learn anything from. So it's somewhat small, but you know, 80% is not too bad. No, it's the other door. Okay, so in graphically, it looks something like data for a month in the beginning, roughly 2 million events, almost 5 million events, mainly Germany, England, a little bit United States, and hopefully throughout time we'll get more of that. We'll get back to that part later on. But that's kind of the initial data set that we started out with when we needed to train this model. So, engine room. So it's time to get your sleeves up and get dirty, so let's dive in and see what happens. So, when you have this data we talked about before, the different cookies, time, location, OS, and device, you can choose to represent it as a graph. So essentially the cookies are the big red dots, and all the different connections you have on the side is how that cookie is associated to the different events over here. And that means you can, when you do this, the task we need to solve boils down to simply cutting that graph up in chunks such that each cluster profile is a user profile. Or cluster cookies is user profiles, right? So that's easy, super easy. And even more easy because there is tons of these graph cutting algorithms out there. We just take one from the open source market, put it in, press play on the laptop, and we're done. Great. But unfortunately, it doesn't work that way. Because in production, things don't scale that well. We might have billions of events, billions of nodes, and billions of edges. Things don't scale that way. I guess you could, if you have infinite money, okay, fine, buy the biggest machines you can get and shitloads of them and go nuts. But it means the whole product will be very expensive. So we thought about that, and we kind of went away from it. We had to do something else. So the problem is scale. What do we do about it? We can't just use the normal stuff we have on our laptops. So the first thing we thought is, okay, can we somehow take that big graph and chunk it up in smaller bits and maybe focus on these smaller bits afterwards individually? Turns out that we could. So we take from the graph, we take the cookies and the IPs, we forget the rest of the metadata that we have. We only look at this. And then we apply a algorithm called connected components, which essentially chucks it up, cuts it up in chunks such that there's no connection between anything. I try to illustrate that here. And sometimes it means you get, this is what I did before, kind of a singleton, which is ignored because it doesn't provide any connections to the rest. In doing so, we might actually introduce an error because we kind of left out the rest of the data. So you could imagine that these two cookies are in fact connected with some other parts in the graph. So we are introducing an error. We don't know how much, but we do it simply because we need to get rid of that scale part, right? So this is kind of what we accept. So the idea is now we are actually able to take the big graph and cut it up in smaller chunks and then focus on dealing with these individually. So we do that. This is what it shows here. And actually there are many different solutions or ways to solve this problem. We tried a whole bunch of these. I'll show you some results later. So right now I'm going to show the result that actually worked. So what actually worked was that we do this pairwise classification between these things. So in this case we got 5 cookies in our example. We create all the different pairs we can get, and we blend it in with the ground truth. So we see the ground truth tells us some are connected, some are not, according to the ground truth, how that works. So we came from the big graph, smaller one, and now we're down to kind of only 2 pairs at a time, right? So in creating a classifier that has to tell us, do these 2 cookies belong together or not? We need to create a classifier. In doing so, we have to create some features that somehow captures the structure of, do these cookies belong together or not? So again, the raw data we have looks like this. So we have to get from here into something that hopefully tells us, do these cookies belong together or not? Some number. So if you look at the data, we'll see that first of all, they don't necessarily have the same number of events, right? Okay, so we can't just do normal stuff with it. So the first thing we do is we make some aggregations. Anything related to time, we split it up in hours and in days. So we kind of get a profile, what is the activity pattern of this particular cookie throughout time. And for the stuff that is belonging to sets, we create 2 sets and we look at some similarity metrics. For the sets, we use the Jakarta index. That is essentially just the overlap between things. And for the distributions we have over here, there's a whole range of different similarity measures. One is cosine, coloration, similarity. They more or less measure the same thing. We just put them in to start with. Possibly we could take some out because they're highly correlated. And we take all these features and we can then combine them into a 26-dimensional feature vector. So that means for every cookie pair, we take all the data associated to these cookies, do our calculations, wind up with 26 numbers in a vector. So one way to handle this data, or look at the data, is to apply this vector space modeling. You know what a vector space model is? Okay, no one, great. So the idea in the vector space model is simply to consider the features here as coordinates in a coordinate system, just like x, y, z you did in high school. No, same thing. So in doing that, that means that every cookie pair doing this calculation, this becomes one point in 26-dimensional space. This is where it becomes a little bit abstract. Of course, we can't see into that space because we only live in a three-dimensional world. There are some tricks around that mathematically you can do. We can apply this principal component analysis. I did that, and I colored the positive and the negative cookies. And as you can see in this subspace of the 26-dimensional space, you see that there is actually some separation between them. So that indicates that the features that we did calculate might work. They actually handle the separation fairly well. You can always argue you could have better separation, that would be great. But if I saw a picture like this and I would see a white cloud and a red cloud on top of each other, then I would be very worried because it might indicate there is no separation at all. So this only shows 2 dimensions. You can imagine the red cloud and the white cloud looking like this, but if they're overlapping or there's actually a distance in the z-axis, I can't see that from the picture. So I don't know if they separate. I can just see there is something going on. So this data is what our classification model sees. It doesn't see this data. It doesn't care. It looks at the aggregations like that. Okay, so we can take that data. We can put it in our classifier. This is a standard tool, gradient boosted decision trees. It works on several different platforms. So this is a slide of how that works. It's called XGBoost. It's very simple to use. So it is essentially during the training phase of the cloud you saw before. It tries to construct a number of trees. We can specify how many, and we can also specify the depth. So it constructs a number of trees that takes each of these features by itself, finds a threshold into its split, and then continues on down the tree. So that means when you train the classifier, what you can do is during serving time or prediction, you take in your features, you take 2 cookies, calculate the 26-dimensional feature, apply it to the system, and it will actually traverse the tree throughout different branches, spit out a number at the end, do some nonlinear mapping, and finally we wind up with a 78% probability that these 2 cookies actually belong together. So that means, and as you can imagine, CPU-wise, this is extremely fast. You take one number and you figure out, is it higher or lower than 1? That's it. Or whatever the threshold is, and you just continue. So it's super fast, and you can parallelize it. So that's very nice to use. Of course, we have a gazillion cookies pairs to do this on, but every cookie pair can be done very fast. Okay, so we started out with the pre-clustering. So we now have, in this case, 7 cookie pairs in our pre-cluster. We did the classification part, and for every cookie pair we got a weight out, a probability that they belong together or not. And that means we can now reconstruct this as a graph again, but this time with weights on it depending on the probability. And this problem we solved before, right? We solved that again by our kinetic components, which means we cut the graph up according to the weights, and hopefully we'll get something that splits up even further, more intelligently based on do the cookies belong together or not. And the final stage we do is we actually do some pruning. I try to show you here with the numbers on it. So how many connections do the different cookie have? 2, 2, 2, 3, and 1. And we do some kind of a cleaning up where we say, let's keep the 95th percentile of connections. So if you have a large cluster like this, for instance, let's say it's a few hundred, and there's one hanging at the end, it probably doesn't belong there. So let's cut it out. And that's what we do here. All right. So this is kind of the story one more time. We start with full graph, split it up into sub-chunks. Each of the sub-chunks, do classification, get the weights out, do the clustering again, looks good, and we do the pruning, and hopefully this will give us, this is a user, this is user, this is probably also a user, right? So each of these chunks run completely parallel, and you can do these as many as you'd like, and you can divide them up any way you want to, which means it becomes very easy for us to distribute across machines. And hopefully we solve the problem of this big monster over here. Okay, so that was the engine room. That was the dark corner of things. So let's look at some performance stuff. Okay, so one of the metrics to evaluate are we good or bad, or what's going on, is precision recall. How many of you guys know precision recall? A few, great. Okay, so I won't go super much into detail of it. I try to visualize what it means. Essentially, you do some prediction and you measure up against a test set what was right, what was wrong. So your precision is precisely how many of the right ones did you get out of the ones you thought you had right. And this is how many right ones did you get out of the true bunch of rights. And then you can do some F1 scoring. These are essentially two different numbers. Usually they kind of correlate independently or traversely such that if precision goes up, recall goes down and the other way around. So what we want is, of course, both of them to be high. That would be awesome. But if you have one metric you need to look up to, people sometimes use the F1 score if they want to. So what it means is, if we try to plot this, is we have precision and we have recall, and the requirements is simply 80, 30%, and then there's the time. I'll get back to that later. So it means that we need performance stuff that lies up in our red triangle up here. Anything outside, we're not in good shape. So that's kind of the idea. So let's see. We did a lot of stuff. I'll focus on this one first. This dot over here is the pre-clustering only, no pairwise stuff. Just the basic part of things. Just chunking it up in basic parts and see how well we're doing. And actually we got pretty close, 79% and somewhat, I don't know, 37% recall, so we are almost in the game. So we thought, perfect, this is easy, super nice, and we got plenty of time left, so why not try all kinds of strange ideas? So we did. And as you can see, everything we did, we kind of fucked it up. So nothing actually worked afterwards. The best result is the most crude one, the most basic one. Everything else we did fucked it up somehow. So, and this does not include the pairwise. So when we saw this picture, we thought, okay, we need to do something. So we looked into the pairwise stuff, and all of a sudden we saw the yellow dots going into the red area. And that means that we can now have a precision recall of something that smells like a victory. So that's nice. And then we included the pruning part. Remember the last part where we kind of cut off the small things at the end? We got a recall and precision even higher. So that's awesome. So we thought, perfect, man. This is great stuff. The problem was that, you know, when we got new data in 2018, we had no clue if the old data set was somehow biased. Was it wrong? Were we lucky? Or what? So now in 2018, which is just 2 weeks ago, we got a new extract of data, and we had to cross our fingers and hope that, you know, things wouldn't fuck up too much. So again, same story one more time, another provider, do stuff again, joining up, get data in. In this case, only 2 weeks of data, 12 million events, 80,000 profiles, and even better distribution, even fewer singletons. That's great. Non-singletons 98%, so more dense data set. Sounds good. So this is what it looks like. Again, this is mainly from Poland, 7 days training, 7 days testing, a few other countries, and hopefully we'll do more of it. And this is extracted just 5 days ago. So it's very, very new. And putting that aside, we got even better recall, right? Mainly because of the density of the data set, meaning we got even more connections and more opportunity to make the right connections afterwards. So that's great. We're looking good so far. So, having that in mind, we couldn't get our arms down with the data science team, right? Because now things work. Now we just have to put it in production, no problem. And then we start hitting a few other walls, right, as always. So, this is the basic sort of flowchart architecture, you can say, of how things work. There are kind of 3 different pillars: training, predicting, and serving. The training part is what we're responsible for in the data science team. This is what we come in. So it takes deterministic data, does all the magic, it spits out the model parameters. This is all done in Python because it doesn't have to be super fast. This is probably something we'll do maybe once a day, maybe every 2 weeks. I don't know, depending on how much things change out there. So it spits out model parameters, sends it over to the prediction part. This has to be somewhat faster. It has to run once a day, and there's shitloads of data, so it has to have some volume. So they reprogrammed it into Scala, some of the stuff. The XGBoost library I mentioned before is already ported to Scala, so there was no need. And that means the model parameters are actually compatible to these things. So it takes much more volume, does the same thing with the model parameters, and spits out the cookie associations for each user. And that is given to the serving team. I actually don't know what goes on up here, except somebody serves it, so we're good. Okay, so one thing is it works on a laptop to get these awesome results we saw before, but we still need to make it work in real life. We still need to work on a substantial amount of data. So the guys, we aim for getting 2 weeks into the pipeline, but realized maybe we'll start small. Let's do 2 days, just to see that things don't break up. So we did that, same story one more time, put in the data, get some stuff out. And then we started seeing that, oops, there were some problems, right? Because some of these pre-clusters, they have more than 1,000 cookies inside. So you can imagine when you start doing cookie pairs of all the combinations of 2 pairs in 1,000 population, then we have problems, right? So and that often happens when you got one IP, like I said, to rule them all. I mean, you can imagine all of us sitting here on the SAS Hotels web and Googling stuff. That goes probably through one IP address. And how many cookies do we have here in the whole conference? So that, I bet, will probably be wind up in this particular part here. So we have to address that. Another problem is that when we start predicting, it took quite some time to do it. And if we want a 24-hour cycle, it doesn't matter if we take 2 days, it doesn't work anymore. So the engineers, they came back and said, it's the features, guys, you have to do something. You got 26 of them, can't you just choose one? What the hell? So we have to look into this and figure out what's the balance between things. Do we strictly need 26? Can we do one, maybe not one, but can we do 20, 25? And can we take out the one that has the toughest load on the systems and still get acceptable performance? I'll get back to that, what that means. So the first one, large pre-clusters, as mentioned, they are super annoying, big. This is the NQS K-curve of 2 and 1,000. And as you can see, anything in the light red area, we're good, we're happy. We can do less than 500,000 cookie pairs. If we're above this, well, for the moment, we have to ignore it. We can't handle it for the moment, so we simply skip it. And that means, of course, that the recall goes down, because there's a whole portion over here that we're not touching. Especially like a conference like this, or a large corporation or something, we can't handle it for the moment. So we're throwing away results that we, for the scalability of it, can't handle for the moment. Okay, so this is addressing the part of having too many features. Now, does anyone know what an ablation study is? No, I didn't. I've been doing machine learning for 15 years. I learned it a week ago or something. But it's apparently the study of precisely figuring out which, in this case, features can we cut and still get the least performance drop. So in this case, what we want to do is we want to focus on the features that is the toughest in production, take it out, and then reevaluate performance and see, are we still good? And then taking that step by step all the way down to having maybe just one feature left. Unfortunately, I didn't get that ranked list from the guys, so I did my own. And this is more or less the same idea, but based on the importance of the model. So it's not entirely the correct analysis. But you see the point is we start from up here, and as we take out features, we'll see a drop and a drop and a drop and a drop and a drop. Now we're still in the red box, so maybe we're good. Maybe we can just accept these. But given we have the opportunity to stay up here, it becomes a trade-off to figure out where exactly do we want to be. We want high precision and maybe pay for extra machines, or do on a lower precision and accept the cost reduction. Don't know. That's a PO decision, essentially. Okay, some challenges. There are always challenges to these things. First of all, the large pre-clusters. I keep getting them up because they are really annoying. But we need to do something about it. We looked into some adding some different things to it in terms of the pre-clustering algorithm, the connected components. It doesn't really work that well, so we still have it out there in the horizon needing to fix. We might want to look into some streaming part of things that might help us out. I'll get back to that as well. And then there's the whole thing I didn't mention yet, this IP obscurity. In Germany, they obscure some of the IP addresses, I think all of them actually. And then obscured means that the last octet in the IP address is either randomized, I don't know, or set to 0, I don't know actually. But it means that when we apply this to our pre-clustering part, the first step of the algorithm, it means that the IP addresses that we heavily rely on, they're not true anymore. So when we do that, we get noisy pre-clusters. Now you see, the initial algorithm might have cut it here, but the truth was there was actually a connection between them. So that means we start putting cookies in different and wrong pre-clusters, meaning noise stuff. So we cut users up that shouldn't be cut, and we combine users that shouldn't be combined. But that's the nature of it. It becomes kind of a cat and mouse game. Yeah, and this is exactly the slide around, right? There is this, obviously these, as you know, these anti-tracking mechanisms out there becoming this cat and mouse game. There's first of all GDPR, a big heavy player. Adform is fully compliant, so it means when stuff winds out on my table, I have a somewhat smaller data set because I can only include data set for training that comes from data that has been given consent by the user. Otherwise, we can't use it. So it limits the data set. The results I just showed you, which is a few weeks old, is all GDPR compliant. So given this limited data set, it smells like we still get something that is reasonable. Apple introduced in Safari some time ago, I'm not sure when, this fake user agent. So you can, I'm not sure if it's default enabled, how it works exactly, but there is an opportunity at least that when Safari spits out the user agent string, it's fake, which means, again, when we rely on this particular information in our algorithm, we get noise. We start connecting stuff that shouldn't be connected and so on. Right, and again, the IP obscurity. So again, this is the cat and mouse game. We do the best we can with the limit of data. They try to limit it, and we'll do the best we can again. So performance is dropping, certainly, as these things gets implemented in the world. Okay, future. Again, split these stupid clusters somehow, figure out a way to do it. We could go random. Say, don't care, this is too big, just cut it up in chunks. See what happens. Introduce noise in that sense, but you know, we have an opportunity to process the data anyway. We might see a drop in precision because we're cutting randomly, but recall could go up, so we can include more in the pool. Could be, we haven't tried. Then there's the streaming part. That's kind of one of my things I'd like to introduce because we talked, I mentioned earlier the whole thing about being faster than 24 hours. So usually some of the external providers that exist already, they have a 24-hour lag. So we give them the cookies, and sometime later the stuff comes back and say these are connected. So that means if you guys browse today, you lose a cookie, the next cookie you get, we can only connect that the day after. That means if you look for rockets yesterday, and today you're interested in shoes, we don't connect these two things because there's a big lag in between. So that means we keep putting ads around rockets, but really you're into shoes now. So we can reduce the time it takes to make the connection, the better. The more we can say, forget the rockets, it's shoes now. So this is kind of one of the ideas we have. Somehow spit in Kafka, maybe there's some streaming parts. Some of these algorithms that I showed you are batch-based, which means they will have to be addressed or rearranged or recoded somehow to make it work. And maybe more features, that would be awesome too. I would like to do some contextual stuff, so we kind of scrape the websites. Is the website really about rockets? Is it really about cigars or Formula 1 cars or shoes or whatever? If we can include that somehow in the profile, we can maybe say there are two cookies, they both look at rockets, maybe it's the same guy. And even if it's not the same guy, the mistake we make is probably small because they're both interested in rockets, or whatever the profile is, right? So it might provide us with some additional information. This, again, is a whole project on its own. It scales even worse than this one because you can imagine there are millions and billions of websites out there that has to be scraped and indexed, and they change all the time and so on. So it's a nightmare from a back-end point of view. But still, it's interesting to look into. Some references. This is some of the stuff we read in the beginning. It's not entirely updated. I'm sure you can find other stuff out there. Once we got the pairwise cookie classification up working, we kind of left this field a little bit. So if you want to engage, you can look into it. And that's it. Even before time.